John's got a background in math and engineering, has done lots of work in software development, previously at Coinbase, but now works at Consensus Diligence, auditing smart contracts. I first found John from some excellent Medium posts that he's written about the topic, and wanted to know more about what he had to say about the Ethereum blockchain. So his presentation today will go over some of the foundational concepts you'll need to understand this field and his estimation of where it's going. So with that, John, take it away.
Check, 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 check. Yeah, we got the mic. How's that? Am I audible? Can you guys hear me? Awesome, amazing, thank you. Okay, without further ado, I present to you a brief history and future, potentially, of smart contract security. Hello, I'm John. Online, I tend to go by Marillion with an underscore after it. I'm a smart contract auditor at Consensus Diligence, and we are part of Consensus, which is a venture production studio building on Ethereum.
John,
yes?
A little bit so it's under your mouth.
So it's under my mouth. Yeah, I mean, I can hold it if I have, just talk like this. Keep letting me know, I guess we'll get there. So I'm gonna try and move quickly. This is what I'm gonna talk about. I'm gonna talk about how we got here, where we are now, and where we might be going in the future. I can see how when I look over here, I'm more audible, aren't I? So the idea, in January 2014, Vitalik Buterin published a white paper describing his idea for Ethereum, a world computer, a next generation blockchain. So if you think of Bitcoin, where Bitcoin has this central concept of unspent transaction outputs, in Ethereum, it's more about state. So what that looks like is state is essentially the accounts. The global state is a mapping of addresses. So in Bitcoin, you have these addresses. In Ethereum, addresses map to accounts with these properties: a nonce, a balance, code, and storage. Important to say this right now, that all data on the Ethereum blockchain is public. It's all out there. Everyone can read it. Anybody running Ethereum has your data in their computer. So there are two important types of accounts. There are contract accounts. Those have the nonce. They have a balance in Ether. They have some code there. That gets interesting. And they have storage values. Non-contract accounts, on the other hand, they're just a nonce and balance. There's no code. There's no storage there. You can think of contracts as being the computer programs in the world program. And you can think of non-contract accounts as being the private key controlled accounts that humans will typically use. No code, no storage. So this is what the bytecode that is stored on chain and belong in the contract looks like. This is the code disassembled into its opcodes. And then the idea of a transaction in Bitcoin, there are transactions you send around Bitcoin value. In Ethereum, a transaction should really be thought of as a state transition, taking us from one place to the next. So a state transition has to affect an account in some way, or else you're not changing the state. So it looks a little bit like this. In this case, we have the same account. It has now it has some storage where it did not previously, and it has a balance. So important concept, sending a transaction to a contract executes its code. So it's, see how that happened? So you are running that code when you send a transaction to that contract. And that contract can then in turn send another transaction to other contracts. Except we call them message calls. But really, for all intents and purposes, you can think of these as transactions as well. So you have a human, he has a boring old non-contract account, and he sends a transaction to a contract, which may send a call to another contract, a couple more contracts, and could send calls to more contracts and more contracts, more. Whoa, what's happening here? So this is a good impetus to keep our, because this is programmable money we have here, right? So we are writing code that sends actual real world value and has real world consequences. So we really need to think about the complexity that we program into our systems and how much is really reasonable and can be reasoned about. This complex process must happen deterministically to keep thousands of nodes around the world in consensus about the state. It's not as easy as it sounds. So how do we build this complex system? So we need a decent specification. So Gavin Wood wrote the yellow paper. This really filled in a lot of gaps in the white paper. Unfortunately, it's really not the friendliest document to read. Instead of pseudocode, he has a preference for essentially hieroglyphs. But it's all there. It's all there, and it could be used to build the system. So we have a pretty good specification. May 2015, so people come together, they're building these systems using the specification. May 2015, the Olympic testnet launches. The testnet this is sort of pre-Ethereum. And testnets are an important concept because there's Ethereum, the mainnet, where all the money is. And then we have this concept of testnets where people really just agree that they're worthless. There's literally, it's the same code. It's the social contract says there's no value on these testnets. So the Olympic testnet predates Ethereum. Now we have a testnet called Ropsten. It's named after a terminus station because it should be your last stop before the mainnet. Security factoid, best practice includes deploying and testing contracts on a testnet first. That makes sense. Staging environment. So Frontier launch, this is the actual Ethereum network, July 2015, with implementations of the client in multiple languages. So we had C++, Python, Go. It's pretty impressive that we have these 3 different implementations completely in agreement about state. It's controversial too. Satoshi said, so much depends on all nodes getting exactly identical results. A second implementation would be a menace to the network. So why do we have multiple implementations? So it's important to think about the trade-off. Multiple implementations reduce the probability of a consensus bug because we're running the code in Python, in Go, in C++. So we're more likely to catch any errors beforehand. But once we're on chain, if any of these nodes go out of sync, we've got real problems. And it does happen from time to time, and it requires some pretty significant community mobilization to get things under control. And so then in our progression, higher level languages begin to appear because nobody wants to write in assembly code. So Solidity, I was surprised, but I looked at the timeline, and as far as I can tell, Solidity was actually the first higher level language to appear. There's this terrible meme that says that Solidity is like JavaScript, and that meme needs to die in a fire. It's nothing like JavaScript. I won't go into that, but LLL, it's sometimes called a low-level language, a lovely little language, a Lisp-like language. All of these things are true. This was released in March 2014. Serpent, this is Vitalik's own creation, is Python-esque, very readable. Also, you should never, ever use it. Serpent was audited a few months ago. We have found the Serpent project to be of very low quality. It is untested, there's very little documentation, and language design is very flawed. It should not be considered safe to use unless many critical problems are fixed. And they're not going to get fixed. It's basically just a throwaway. And so the ecosystem, this slide is meant to entail that look how much is happening and the ecosystem is maturing. This is an interesting story. So how many people are familiar with the DAO? Okay. How many people know what the DAO really actually was and what happened to it? Okay, good. So there's a point to this. Great. So the DAO is a digital, decentralized, autonomous organization, a form of investor-directed venture capital fund. So what that means is we put these contracts on chain and people can buy into this system, and then they become investors, and also they have control over that system and they can decide where the money goes and they get a stake in that. And this is evidently the best idea ever, and we're all going to get really rich. People put $130 million worth of Ether into this system, breaking all records. And at the time, I don't recall, but it was a tremendous portion, perhaps something like 10% of the, yes, I'm correct, something like 10% of all the Ether in existence. And this drove the price up. I mean, for one reason, you're just locking the funds there. You can't sell it. It's stuck in the contract for now. And then everything went to hell. So this price crash was a result of a hacking of more than $50 million from the DAO. So what happened there? First, a brief diversion. I'm going to cover really quickly some smart contract security essentials. So one very important concept, we have gas. This solves the halting problem on the world computer. When everybody is on the same computer running the same programs or can publish their own programs, how do you prevent people from publishing things that will run in an infinite loop? Gas, you meter the instructions, the operations. So if you want to add, that's going to cost you 3 gas. If you want to load something from storage, that's going to be 200 gas. If you want to create a new contract, that's 32,000 gas. So this is how, if your code is too complex, it's eventually going to run out of gas. This concept is somewhat analogous to fees in Bitcoin. So you pay this, you pay it in Ether when you initiate the contract. Gas. And then an important concept is that each block, so it's a blockchain, roughly every 13, 15 seconds in Ethereum we have a new block, but there's a maximum amount of computation you can do in a block, and that's about 7.5 million gas. Delegate calls. So new concept, delegate calls. This is a form of code reuse on chain. So a delegate call would be contract A can delegate call to contract B, and what that does is it runs the code from B in the context of A. So A has this state, it has a balance of 1 Ether, it has these storage values, but it will so the code in B will run as if it has these environmental variables within it. The way I like to think of it is A says, hey, B, what would you do if you were me? And B says, these instructions, please. Those might not even be valid opcodes, I don't know. Self-destruct, important concept. Some contracts can destroy themselves. If you put that instruction in a contract and call it in a future date, it will just delete itself from the chain. And then re-entry. So this is recursion that can happen on Ethereum. And I'm not going to go in depth here, but let's think of it like this. So you've got a victim contract. So we've got this victim contract and an attacker here. So the attacker is going to call withdraw. The attacker, we assume, has a balance of some sort. So then this contract will say, okay, well, what's your balance? Okay, cool. Yeah, go ahead. You can withdraw that. And then this call, message.sender.call, it calls out to here, and the attacker, so it gets the value it asked for, and then it goes ahead and calls back in because the victim has not decremented the balance of the attacker yet. So that just having those 2 lines out of order ruins everything. It's a very subtle mistake, and it wasn't something that we really were aware of from the outset. This is a great blog post published on June 9th that really described the problem. I think that this is one of the first places where it was brought to light. I think there's some great GitHub issues to be read as well. So it was about a week later, someone read this thoroughly, put their stuff together, and started emptying the contract. It was a very exciting day. And so this is just an interesting aside, but this is sort of like a security kind of emergent property where the community, there's this group of people called the White Hat, the WHG, the White Hat group. And whenever there's a hack, they kind of just show up and try to out-hack the hackers. So they saw what was happening, And they mobilized and started also emptying the DAO, stealing the funds, put it into a safe place, and eventually returned it to people as much as possible. Another consequence of this was the DAO fork. So the community was tremendously split about how to handle all these stolen funds. It wasn't all returned. So ultimately, a consensus change, a change was made to the consensus algorithm. This split the chain. We get these two different chains, these two different histories, these two different communities emerge out of it. It's fascinating. Okay, so more recently, I'm going to do the second parity hack. I took the first one out. So multi-sig contract, multiple people can put their funds into a contract together and say require 4 out of 5 or some M of N to make a withdrawal. And the parity multi-sig contract, most of the actual functioning code was a secondary contract, a central contract, which all these other instances of the multi-sig, of the parity multi-sig contract would call for instructions to handle the calls that it got. The flaw was that this library could self-destruct. And there was a fair, I won't go into it, but it was really quite sad. It cost about $230 million. And now this wallet is like, what do I do? Where's my instructions? So all this money is frozen in these wallets. It's not moving anytime soon. So quickly though, I like to say this is not stupidity. These are excellent developers. The parity team are really incredible developers building really incredible software and cutting some corners and not being very careful in this case. Yeah. So what a journey. That's where we've been. That gives you a sense of the history. It informs the culture. It informs the security practices around the Ethereum blockchain. And I'm going to talk a little bit about what we have today. It's going to be pretty quick. Other speakers will probably go into more detail. So Solidity. Solidity has recently been audited. It was found to be pretty solid. So we have a pretty good compiler. Best practices. These are the consensus best practices. This is a community managed set of documentation. It encodes all the best practices that we know for putting secure code on the Ethereum blockchain. We've got some great reusable Solidity frameworks out there. 2 excellent teams building really good reusable code. We have this tool called Mithril. It's a static analysis tool. You'll learn more from Mark about what that really means under the hood. But this is great. It's fun to use, and it sort of breaks down the pathways in your code. Emerging languages. This is like, to me, this is really sexy just because I get really excited about different ways of targeting the EVM with a human readable language. So Bamboo is a project of Yoichi. Dr. Yoichi at the foundation makes state transitions explicit and avoids reentrance problems by default. So it's really basically a built-in state machine, and apparently you can't pull off reentrancy. Viper is the spiritual successor to Serpent. It is another Python-esque language. It's an experimental program language that aims for some of the following goals: security, simplicity, auditability. It is in the process of being formally specified. I'll talk quickly about that a little bit later, but I'm very excited about the future of Viper. Babbage is a mechanical smart contract layer, so you can drag and drop and like program your language like this. I don't know if you would call this a domain-specific language, but it's one of what I believe will be more domain-specific languages coming, if that's what this is. Formal verification. This is it's new to me in security, but it seems to be coming out of academia, and Ethereum is really driving, I think, a lot of research in formal verification. So that's very exciting to me. So formal verification, in essence, is by developing a rigorous model of the language, including EVM state transitions, you can prove higher level properties about the EVM code with respect to the model. So basically, you can do math and prove theorems to say, yeah, this bad state in which that you never want your contract system to get to, that's impossible. It is unreachable. So great project, KEVM. They're doing wonderful things, and they intend to extend their verification up to Viper so that we'd have right from Viper down to the EVM. ETH Isabel, this is another exciting project, and somebody at Consensus is currently working on something that would take LLL to the EVM through a formally verified pathway. So also very exciting. On-chain privacy. I said before we don't have it. We recently kind of got it. So we have these primitives that are available to us now. They're very, very expensive in terms of gas, but they enable us to do really great things. So if you're familiar with Zcash, this gives us zero knowledge proofs, ZK snarks. Honestly, I don't know how people are going to use it yet, but they'll figure out some cool stuff, I'm sure. Ring signatures as well. So shout out to another blockchain, Monero, that does ring signatures and privacy that way quite effectively. I think I'm wrapping it up now. Yes. So this is, to me, I'm still sort of formulating what this really means, but where I think it's all going is towards these three pillars of making the Ethereum blockchain really work and fulfill its mission. So that means correctness. The code does what it does, what the developer thinks it does. It's transparency. Clarity might be a better term for this. This means like my mom knows what the contract's going to do. And then she actually trusts that it will do that thing. And once we're able to unlock those things, I think we really will see the potential for these fascinating, interesting new models of collaboration come to fruition. And so we're hiring. We're right at the center of the action. We're Consensus. Everything we do is on Ethereum. And Tom, talk to him as well if you'd like. Thank you very much, everybody. That's my talk.
Anybody want to ask John a question before we switch over?
Did I not go over time?
Yeah.
Amazing. Oh. Oh, okay. Does somebody actually have a question? I don't know if this is on even. Sorry. Sorry.
Yes.
I'm
I totally
sorry.
messed that up. So how exactly is your mom supposed to know what a contract is going to do? Like where's the translation there?
There's a reason that was one slide or one line on the last slide.
But I'm kind of curious.
Yeah, no. So in my mind, it's something like Rap Genius. I don't know. There's some way that we make it without that, like people develop trust in their ability to explain what a contract does to normal people. I could be wrong about that, but. Sorry, did you want to challenge me?
No, I'm good. I was just hoping that there was some more there as far as like a translation of common language, right?
It's vaporware in my mind. Yeah. No, we got to get there. I don't know what it is though. Fair enough. Brendan.
Yeah. What's the deal with CryptoKitties and scaling?
Okay. Question is CryptoKitties and scaling. I mean, it's a massive contract system, and as far as I understand it, it creates contracts. That's a really expensive thing to do, and every contract has like kitties have a lot of. They're very stateful because it's like, you know, how long is their hair and what color is it? So you have to be able to track all of these variables, and that's the most expensive thing you can do on chain. I think like gas optimization is a fascinating, very fun thing, and we're just gonna have to do more of it. And there's gonna be a lot of other kind of scaling work to be done. It's not my forte.
I think that's all we got time for. So find him at the bar. Thank you, John, again.
Thank you, Dan.
For the introduction tonight.